So thanks very much to the organizers for inviting me. So I'm going to, also thanks a lot to Josh for preparing. I mean, he's going to be very helpful. I'm trying to, I've written just moduli spaces, but it mostly will be geared towards GIT. I will try to not, I mean, this won't be a course on stacks. If you want to learn more about stacks, I'm happy to answer any questions, and please ask. I'll try to keep the technicalities as small as possible. But I would like to just give a definition of a stack first. So when you think of a scheme, you should not think of it as a local ring space, etc., but you should think of it as a functor from let's say, affine schemes to sets, or schemes if you like, but then it's kind of a tautological definition. But you should think of it as functor of points, so morphisms from T to X. And this should also be a sheaf. Sheaf, and there should exist an Zariski atlas, by which I mean that we can write this as a union of affine schemes. So this is what a scheme will be. When you think of stack, you should think of scheme as a functor rather than as a space. And then, so when you do GIT, you're mostly working with projective, quasi-projective affine varieties. But if you want to take a stack perspective, you are kind of forced to also deal with algebraic spaces. So let me just say that an algebraic space, I mean, just to have the word, it's a functor which has some sheaf property. So as above, but we now there should exist an Ital atlas, by which now this open part of the scheme now is going to be in Ital maps. So we have an Ital surjective map. So algebraic spaces are just some kind of mild generalization of schemes. If you have never seen them, don't worry, and it won't really be, but here's the definition. But now for this series of lectures, we're going to use algebraic stacks. So an algebraic stack so it's a functor again from say schemes or affine schemes or your favorite thing, but now we have to take values in groupoids. Which again is some kind of sheaf condition, which I don't want to go into, and then also the existence of a smooth atlas. So there should be some affine schemes together with a smooth surjective map to my stack here. And I'm going to try to always denote stacks with curly letters. So there's two differences here. I mean, the first is the kind of the crucial thing is that we're working with groupoids instead of sets. So let me give an example. So if we do moduli of curves, this is going to be a functor that on a scheme T gives me families of smooth projective genus G curves over T. But I don't want to consider this as a set, but I want to remember like automorphisms of curves. So the kind of precise way is that I say that objects are these proper flat family of genus G curves. But then I also want to have morphisms. So a morphism from C1 to C2 is going to be an isomorphism relative to T. And the most interesting thing here is that if I look at the morphism between C and C itself, I get the automorphism C. So this stack, this functor, it remembers not only, I mean, it contains the data of automorphisms. And being a groupoid, I mean, groupoid is just a fancy name for a category where every arrow is invertible. So that's here. The morphisms of this category are all invertibles because I can always turn these arrows. So so here it's not clear that this has an atlas. So, but it does have an atlas. So for example, if you have yes, let's do the case of genus 1 curves, let's say over the complex numbers. Then we can do the Weierstrass. So every elliptic curve. Oh, okay. So now I do elliptic curves. It's actually not just in genus 1, but so then it's actually marked with 1 point. But I can write every elliptic curve. I have the Weierstrass form. So that gives me a map from I guess minus 0, 1. So here I take some lambda and send it to the curve given by y squared equals x times x minus 1 x minus lambda. So this is going to be a smooth atlas in the case of elliptic curves. Okay. So these are an example of an algebraic stack. But all stacks that we will see will be eventually quotient stacks. So, but before going to quotient stacks, let me tell you what you really need to know about stacks. And there's 2 things. So, and the first one is that there exists an underlying or an associated topological space and one can define this as the set of all k points. So we think of I mean, if we pick a field k, spec k mapped to x, that's what we think was a point. But we have to identify if I pick a bigger field, that's going to be the same point if I just increase this. So I'm modding out an equivalence here, just as we would do if we would do a scheme. I could take the residual field, but for a stack, you don't have a residual field in the same way. So we take all fields, all maps, and then we mod out by some suitable equivalence. And you can also put a topology in this, making it a topological space. And the second thing is that, as I allude to here, this functor remembers automorphisms of our objects. So when I pick a point of my stack, it's going to have some automorphisms. But here, it's not enough to just pick a point of this set, but I really have to pick a representative. So if I pick a point in the sense of a map from spec K, this gives me what I call the automorphism group scheme of X. So it's a group scheme over spec K. So as a first approximation, a stack is a space together with roughly a group for every point. And we are mostly going to be interested in kind of GIT-like stacks where we are not assuming semi-stable equals stable. So we will have infinite groups. But there's also a notion when you have finite groups, it's an important situation, like when stability equals semi-stability. So we say that X is doing Mumford if for all points, so being vague here, but for every point here I can choose such a lift. The automorphism is in the child group scheme. So which just means finite if you are in character 0. So please think about just the complex numbers, character 0. But if you're interested in positive characteristic, there's a slight difference between Lee-Mumford having a tal automorphism groups and just having finite automorphism groups. So you can have things like mu p and alpha p in positive characteristic. And it turns out that having finite automorphism, tal automorphism groups are actually the same as requiring that instead of having a smooth atlas here, you can also do with an étale atlas. So more mimicking the case of algebraic spaces. Here, having a étale atlas is equivalent with having a smooth atlas. But here there's a difference. To accommodate for infinite stabilizers, you have to have a smooth atlas. If you're just happy doing finite stabilizers, you can do an étale atlas. And this is an example of an étale atlas. It's not merely smooth, but it's étale. Okay, but to tie this now back to kind of Josh talk and so on, let's do quotient stacks. And essentially all stacks that I write down will be quotient stacks of one form or another. So start with a group scheme, just a linear algebraic group, say. Acting on some scheme. Then there's a way of producing a stack that we call X mod G, but we put these brackets around it, so it's going to be an algebraic stack. And it's going to come with an atlas, like a preferred atlas to this stack. So it has an atlas which is mapped from X to X mod G. So I'll call this P. And if G is a smooth group, this will be a smooth atlas. If G is an étale group, this will be an étale atlas. In positive characteristic, G might be non-reduced, and then this will just be a flat atlas, but it's actually also here okay to just have a flat atlas. So it turns out that having a more complicated atlas, you can then go around and cook up a smooth atlas. So now let me do the dictionary here between these algebraic stacks of this special form and G-equivariant geometry of X. So the quotient stack we call curly X and G-equivariant geometry of X. So the first thing is this topological space of the stack X. So this is nothing but G orbits of X. And the dictionary goes as follows. If I have a point of my stack here, well, I'm going to let's put the G orbits here. So if I have a point of my stack, this corresponds to the inverse image of X under this atlas. So the fibers of this are G orbits. If I have a point spanning an orbit, I can just take the image of this. So that's the topological space of my stack. It's just it's an orbit space of X. Now the automorphism group of a point of my stack X is equal to the stabilizer group of a corresponding point. So let's say that here take P of X. So the stabilizer group, I mean, it comes canonically as a subgroup of G. This automorphism group, which is associated to just picking a point here, does not remember G. So the thing is that the stack curly X does not really know about G. For example, if G acts freely on X, then there are no automorphism groups here, and you can't recover G from X. So this does not come as embedded into G, and you can see it from this side that if I take, so if I would take another point in the same G orbit, then this is only conjugate to step X. This is a conjugate subgroup. So this is why here there's no preferred way of putting this into G. So I have to pick a pre-image of my orbit. So pick a point in my orbit to get it as a subgroup of G. And the whole kind of philosophy of working with a stack is that you're forgetting about the specific action of G, but you're instead just remembering kind of the quotient, remembering the orbits, and you can't get this finer information as where the stabilizers live in. And then a coherent sheaf on the stack, or a coarse-coherent sheaf on X, it's going to be the same thing as a coherent or coarse-coherent sheaf on X, together with a G linearization. And this you can also you can see how these are related by simply pulling back your sheaf. So if you have a sheaf on your stack, you can pull it back to the atlas. And that's going to become equipped with a G action. And conversely, if you pick a sheaf here and dough it with a G action, it descends to the stack. And if we want to take global sections of a sheaf on X, that's the same thing as taking global sections of this pullback and then taking G invariance.
Are you making any assumptions in the group?
Here there are no assumptions on G so far. I mean, you can.
Any group.
Right. So if you're working over a field, you take your favorite group scheme. If you would work over some base, you would have to take a flat group scheme.
And you're writing global sections over like X, which is not curly.
Oh, sorry. This is with curl X. Yes. Thanks. But the point here is that all kind of geometry on the stack can be described in terms of equivariant geometry on X if you have chosen this quotient presentation of your stack. But X itself, does not remember about G. So this equality here, or this isomorphism, is extra data on X. So,
but you haven't actually defined the quotient stack yet.
I haven't told you what it is. So perhaps I could do it here. So I would need to say what a t-point is. So a t-point comes equipped with a g-torsor and a g-equivariant map to X. These are the objects, and then you have isomorphism of g-torsor compatible with this as your arrows. So when I define this one, then this is defined in terms of G, but I can think of this just as a functor, and then this functor does not remember about G.
Can I ask? The category of stacks is famously not just the category, but the two categories.
Yes.
Is this the choice of the presentation in some sense killing off the need for
Right. So this thing is equivalent to giving a map from X to point mod G, so BG, and this map is all the stackiness is contained here. So this is what one calls a representable map. So this is represented by a scheme. So if I take the atlas of BG here, then this is Cartesian. So writing my stack as a quotient of X by an action of G is equivalent by giving this map. And this map is represented, which means that if I think of all the stacks over BG, that's just one category. So if I fix my BG and just consider stacks over BG, that is G equivariant geometry, and that's a one category thing. But then when I just focus on the stack X and forget about G, then I'm left with just X, and then I have two categories. But, that's kind of unfortunate. Okay. So let's do some examples of quotient stacks, and let's start with this point mod G. So then the topological space is as I said, this is point mod G. So I have just one orbit. So the underlying space is just a one-point space. And if I pick an automorphism of an object, then I get G. So it's a 1 point with a kind of G worth of automorphisms. And if one looks at this formula for T points, now I'll just have G torsors. And the reason that I have a 1 point space here, that if I work over an algebraically closed field, then all the G torsors will be trivial. So it's only a trivial G torsor. Okay. And then if we do something like an plus 1 minus 0 mod gm, this will just be Pn. and my atlas in this case is just the universal G entorser. Yes, I guess I never said that, but also this atlas, the atlas is a G torser. So what this means is that, like in PN, PN is a free quotient by a free action of GM, but in general, even if the action is not free, this atlas will look like the atlas of PN. It look like if the action was free. So the idea behind stacks is that when you take quotients, they behave as if they were free. So
Sorry, so if you're saying that the quotient stack doesn't remember G, and if I write down two quotient stacks, is there some easy way to say when they're isomorphic?
well, you can write down what it would mean for if I have a quotient attack by G and a quotient attack by H, what it would mean for them to be isomorphic, but it might be difficult to. Let's say, for example, that G acts freely, then it just isomorphs the two schemes, and it's not necessarily that. If you're starting the G equivariant map between, if you have the same G acting on both sides, and you have a G equivariant map that induces a map on the stacks, but you might have many maps between stacks which does not come from a G equivariant map of these particular presentations. So when you have picked this G presentation, you're kind of locked into just thinking about everything in terms of this G. But from the stacks perspective, you can forget about G, and then you can have more maps. So if we started out mildly, so this was kind of very stacky. This was no stackiness at all, no automorphisms. But we could do like weighted projective stacks. So let's say they had GM acting on with weights D1 to Dn. Then we get the weighted projective stack. So D1, D2. And this has finite automorphisms. So let's do a concrete example. Let's say I take weights 2, 3, and 6. So let's say this is, okay, x1. Then when x1 is 0, here I'm acting by, all these are acting trivially by third roots of unity. So here I'll have the automorphism will be third roots of unity. If I pick x2 equals 0, then this is 0, and I'm acting here by, the second roots of unity, plus minus 1 acts trivially. So here I have mu2, and if both x1 and x2 are 0, I will have a sixth root of unity stabilizing here. But if x3 is non-zero, then I'm not going to have, if x1 and x2 are non-zero, it's going to act freely. So the usual weighted projective scheme is, weighted projective space is going to be a core space of this stack. So this stack is smooth. So these are always, it's always smooth. Because it's a quotient of a smooth scheme by a group, and such stack quotients are always smooth. All right, questions? So let's do one more example, which is going to be important. So this is the kind of the easiest, simplest stack, which does not have finite stabilizers, and which is, well, BG is interesting, but this is the second interesting one. And this is the stack which usually called, or nowadays called theta. So this is A1 mod GM. So here GMX by weight 1. So just by scaling. And now we have two orbits. We have the origin, which has stabilizer the whole GM, C star, if you like. And then we have the other orbit, which is G times, well, let's say X. And this has trivial stabilizer. So it means that this stack, if I draw the space of this, it has 2 points, which I call 0 and 1. And 1 is going to be an open point. So I didn't tell you, but a set here is open if and only if its inverse image is open. So if I pick a set of orbits, that set is open if and only if the set of orbits is open. So this is open and this is closed. And so this specializes to this point. And here I have the GM. Well, let me draw. It's not so legible. So another way of drawing this is like a BGM and a point. And the kind of idea behind this using theta is that one could also think of this as having like a BGM surrounded by this other point that specializes to this BGM. So if, for example, you would think of A1, you would take the complex plane, and instead of taking GM, you would just take R star, then it would literally look like this. All right. And we're also soon going to see the examples that Josh had in his first lecture, I think. So I will soon tell you about good moduli spaces, but let me just say a few words on coarse moduli spaces. So I'm not sure this word was mentioned, but it was implicit in the Jacobo's lecture on K-stability, these properties 1 and 2. So a coarse moduli space to the stack X is a map from the stack to a space. And so actually an algebraic space or scheme, but in general we'll just have an algebraic space. So this is where really algebraic spaces becomes necessary to get a good theory of things like coarse moduli spaces. Such that it should be a homomorphism, so this topological space of curly X should be the same as the topological space of this coarse space. I'll try to denote my coarse spaces and good spaces with bold-faced letters. So I want this to be a homomorphism, but I also want it to be a homomorphism after arbitrary base change. So otherwise I could have something like a field extension here, which I don't want to allow. So I want this to be a universal homomorphism. So I mean, Josh talked about geometric quotients, so if this is a homomorphism, then now the points of my x, if this is a quotient stack, this will really be the orbits of my action. So bijective plus a little bit more, right? And then I want this to be initial. So a categorical quotient. So what I mean by this is that if any other map from a stack to a scheme or an algebraic space, I want this to factor through this pi. So perhaps this will be, I might touch upon this in following lectures. So when you do this categorical and you are only doing schemes here, you're missing out some important things in the definitions of like the good quotient that Josh mentioned. So we see that Josh said that, well, you have a good quotient, you're going to get a categorical quotient. But this is actually leaving out a bit here when you're using algebraic spaces. But that's kind of a subtlety that might appear later. But this is so if X is a quotient stack and this is a core space, then X to this is a geometric quotient. So it's just a reformulation of a geometric quotient without mentioning a group G. So there's no group G appearing in this definition.
I think versions of this definition, like, for example, instead of 1, you ask for, you take all algebraic closures.
Right.
And bijecting.
Right. So that would say that you're universally bijective. So this is just slightly. But in particular, this implies that you have this quality for algebraic closed fields. Yeah,
equivalent class.
What?
Equivalence.
With a right. So let's say pi naught of this. Yeah.
In this definition, why is algebraic space?
Here, why for all algebraic spaces and all maps. So you want this to be the best approximation of a map from a stack to an algebraic space. So if we just would think of functors, there's always a functor that does this by just taking equivalence classes. So if you define like MG, and you would just say that I think of now the equivalence classes of curves, that gives me a functor which is the best approximation, but that won't be an algebraic thing. So this coarse things will be coarser than just taking the associated isomorphism classes. Yeah.
Is this definition closed to the base?
No. So it might happen that you, like in positive characteristic, it frequently happens that you have core spaces that when base change, they're no longer core spaces. So 1 is stable under base change, but 2 need not be. It's always going to be stable under passing to open. But typically it's going to be stable under like a tau or smooth or flat base change. So typically in positive characteristic, sometimes only stable under flat base change. Character 0 usually stable under arbitrary base change. So examples of coarse moduli spaces, well, we have the MG has an underlying or a core space associated to it. Let's see what else I have. Well, we have the case of BG. The point we have this weighted projective stacks, and if I take the associated projective scheme, it's going to be a core space. If I have certain quotient stacks, I can take the quotients, and this works if, for example, G is finite and acting on X quasi projective. So then this is this exists, and this quasi projective. But even if I have a smooth scheme, I might have a finite action on a smooth scheme such that the quotient is not a scheme. So that's where you need algebraic spaces. So if instead here X is a separated algebraic space, and it exists and is a separated algebraic space. So even just thinking about finite quotients, finite groups acting on smooth separated schemes, you still need algebraic spaces. But this also shows that algebraic spaces is a big enough to contain most quotients of finite groups.
So if I look at, for example, your topmost example of the moduli of genus G curves, right? So I guess I'm a little confused about what data I'm trying to encode with the stack. So if the way I would have thought of it is that the non-stack MG is this is some thing that parameterizes the genus G curves.
Yeah, but this is not a fine moduli space. It's just a coarse moduli space. So it's true that for points, for algebraic closed fields, their parameters are the same thing. But if I take a family and try to parameterize a family of curves, so the MG itself does not carry a universal family of curves.
I see.
So if I want to
right. So in situations where you get a fine moduli space,
yeah,
then the stack doesn't really have any.
If it has, having a fine moduli space is exactly saying that these are the same, that this is already going to be a space.
Okay, I see.
So, but what happens here is that you have, whenever you have an object with an automorphism, you can put it into an isotrivial family. So you can twist your thing by this automorphism to get a family where all fibers are isomorphic, but the family itself is not trivial. And such a thing cannot arise from here. All right, so let me go on to good moduli spaces. So this is what's going to be related to GIT. Well, when we have strictly semi-stable objects, so another example here would be to have G reductive acting on X projective, and you take the stable locus, then as Josh said, then there exists a geometric quotient, and this is going to be a quasi-projective scheme, and this is also going to be a core space. So if you're just interested in the situation of GIT when semi-stability equals stability, so then we would also get a projective thing here. But if you're interested in GIT in a situation where semi-stability is not equal to stability, we need to have some more general moduli spaces. And these are what's known as good moduli spaces. So this was defined by Jared Alper in I guess 15 years ago. So a good moduli space for an algebraic stack X. So it's again a map from X to some algebraic space. That's trying to be as close as possible to X. And well, let me, so the most important property here is that the push forward of coarse-grained sheaves from the stack to the space is exact. Let me start by writing this. So the push forward factor from coarse-grained sheaves on the stack to this good moduli space is exact. But to even have a well-defined push forward of coarse-grained sheaves, we at least need to not be completely crazy. So we want this to be coarse compact and also coarse separated. But this is essentially always going to be fulfilled, except that you might have natural moduli spaces where you're not bounded, where you're not coarse compact. So boundedness is a really important property of that. You want the stacks to be kind of finite type at least over the space, over the good moduli space. And then finally, we also want the unit. So the structure sheaf of the space should be equal to the push forward of the structure sheaf of the stack. So let's see how this connects to GIT. And now, Josh only talked about GIT in characteristic 0.
Do these three imply obviously there is a coarse moduli space, or doesn't it have to?
No, so some coarse moduli spaces will be good moduli spaces, but good moduli spaces typically won't be coarse moduli spaces. So that these are weaker than these.
So will all coarse be good?
In characteristic 0.
Huh?
In characteristic 0. Well, not even characteristic 0 as I have written it up here. So again, there's this like BGA would be to a point. I said that BG to a point is always a coarse space. BGA to a point will be a coarse space, but it won't be a good space.
So the answer is no.
So the answer is no. But morally coarse spaces are good spaces. Yeah. But yeah, I'll try to make that more precise.
Does the problem arise when G is non-reductive?
Yeah, the problem has to do with kind of non-reductive gerbs, essentially. So if you have finite stabilizers, finite automorphism groups, a coarse space with finite automorphism groups in characteristic 0 is a good space. Okay, but let's analyze this situation. So when is this? A good moduli space. So let's see what the conditions says. Coarse compactness, it's just 1 point, so it's coarse compact. Coarse separateness will tell you that G is a finite type group scheme. So I'm not allowed to have something like Z. So I should have G finite type group scheme. This is over a point, all group schemes are separated, so that's fine. So this is kind of 0. So 1 here tells me that push forward of coarse-grained sheaves on BG to coarse-grained sheaves on the point should be exact. So let's unfold what this means. So I just erased the dictionary, but it's kind of reminiscent here. coarse-grained sheaves on the stacks are G-equivariant coarse-grained sheaves on the atlas, which is just a point in this case. So these are, and a coarse-grained sheaf on a point, that's just vector spaces. And here I have vector space with G action, so these are just G representations. So my functor takes a G representation and gives me a vector space. So what is this functor? Well, it's essentially just the global section functor. And I said that the global section functor, it starts with a sheaf on a stack, pulls it back, and takes G invariance. So what it does here is take a G equivariant sheaf, treats it as now just something on the atlas, which has a vector space, and then take G invariance. So this functor takes a representation and sends it to its invariant subspace. And as Josh said, this is exact precisely when G is reductive, and if you want to be precise, it's when G is linearly reductive. So this is the thing that I think also Josh mentioned in passing, that in general there's reductive, linear reductive, geometric reductive, and linear reductive is this exactness of taking invariance, or the complete reducibility of finite dimensional representations. And 2 in this case, it will, I'm just taking the push forward of the trivial representation, which is just, so this is no condition. So here we say the BG has a good moduli space exactly when G is reductive, or linear reductive. So if you remember, Josh also talked about, reductive being the same thing as not having a trivial unipotent radical. So that's definition of reductive also in positive characteristic. So this, I think, in characteristic 0, these are the same. So we also saw affine GIT, was it today or yesterday? Oh. So what do we have here? So now I have a reductive group acting on an affine scheme. And I'm again taking my X as this quotient stack. And now I want to convince you that I have a map from this quotient stack to this GIT quotient, which is the spec of the invariant ring of A. And I claim that this is a good moduli space. And again, I have to put in here linearly reductive to be precise. And the argument is about the same. It's going to, now my push forward of is going to go from really, let's say modules, A modules with a G action, and they're going to push forward to modules under the invariant ring, which is just I think of an A module also as an AG module, and I forget about the G action. But no, sorry, I take an A module with a G action, and I take its invariance. Let's say as a vector space, but that also carries a structure as an AG module. This is functor, but exactness can be checked on the level of representations, and on the level of representation it's exact. So this is also exact. But now this second condition Now we see that now if I take the trivial representation, or it's not the structure sheaf A, and I take its image, it's going to be AG. So if I would not have this condition 2, then I could have just taken the map to a point, and it would still be exact, but it would not have the right structure sheaf. So you could also, it's also true that projective, I'll skip this, but also projective GIT, it will give you that we take the semi-stable locus of this projective X. It's going to be a geometric, a good moduli space.
Can I ask, does that work equally well if X is quasi-projective?
What?
Does that last example work equally well if X is quasi-projective?
Well, like projective over affine is fine. It also works with co-projective, but you have to do the right definition of semi-stable. So to say that you take these invariant functions, but you have to ensure that you have an affine open of them. But it works in the same way. And the reason here is really that Zariski locally on here, projective GIT is just affine GIT, as Josh explained. So this is really a kind of global version of this. And these conditions are really local on the quotient. We can verify exactness locally on X, and we can verify this isomorphism of functions also locally on X. But let me finish by mentioning that the good moduli spaces are as good as those that Josh talked about. So let me perhaps, So I will usually abbreviate good moduli spaces by GMS, and coarse moduli spaces by CMS. So what I will say here is that they are the analog of good quotients. So Josh did not phrase it exactly this way, but So the first part is that this map pi is closed, and it's even closed after base change, so it's universally closed. And secondly, for all the point in the core space in the good moduli space, there exists a unique closed point, which I will try to call X naught in the fiber of X. So Josh talked about if you have two distinct closed orbits, then they will be distinct in the image. And this is exactly saying the same thing. A closed orbit is going to correspond to a closed point of the stack, and I'm saying that for that there's exactly a unique closed orbit above every point in the good moduli space. Perhaps it would be good to finish with this example that Josh had, where we have weights plus minus 1. So we have this action, and I said the picture is that you have we have this some special orbits, and then we kind of have the generic orbit. And then we have the it seems that I'm out of colors. And we also have the origin. And so this is the picture of this is a picture of A2. And if I want to draw the picture of my stack, A2 mod GM, I'm just replacing the orbits with 1 point each. But we now see that these yellow and purple orbits, they are specializing to this green orbit. They are not closed, they're just locally closed. And then I have all these other orbits, which are, for some t, I have this hyperbola xy equals t. So this is the picture of the stack. And you see here that we have 3 points. And if I take the GIT quotient, this, which is the invariant ring, well, it's going to be the affine line. So it's spec KT, and here the map is that T goes to the invariant XY. So we see that if we pick 0, then we have 3 points in the preimage. So Josh told us we have to identify these 3 points because these 2 are not closed, but they specialize this closed orbit. So if this is my X, then this green is my X, and this is the unique closed orbit. So in terms of JT, this is usually called the polystable point. But this is just locally closed. This is locally closed. Well, in the fibers, they are open in this case. So good moduli spaces, they have the same good topological property as GIT quotients. And we'll see that they're even closely related to GIT quotients in the next lecture.
Are there any questions?
So Andres?
Just to clarify, you said that with this definition, this is stable on the flat base.
No, I can't claim that. I think no. So, no, but I was saying that in all the thing is that you usually don't verify something like this. So usually you verify something else, and those other things that you verify, I mean, they're almost always stable on the flat base change. But if they don't, I mean, they will be very, very kind of bad core spaces. So I would say that this definition is not quite the correct one. Whereas this is a very nice stable, and there's the better version of this would be say that you have a finite inertia stack. So you have the Kiel-Moore theorem.
There are no more questions. Thank you again.